Every black hole anyone has ever confirmed belongs to one of four weight classes, plus a fifth that may not exist. Here's the whole ladder before we climb it. Primordial black holes, if they're real, could carry the weight of a mountain inside a horizon narrower than an atom, and nobody has ever found one. Stellar mass black holes begin somewhere between 2 and 3 times the Sun and run up to a few dozen, and they're what a dead star's core leaves behind. Intermediate ones, hundreds to tens of thousands of solar masses, spent decades missing from the catalogue entirely. Supermassive black holes anchor galaxies, and the one at the middle of ours holds about 4.3 million suns. Above a few billion sits the ultramassive class, and its poster child is a quasar first caught on a photographic plate in Mexico in 1957. Tons 618. Its black hole weighs somewhere between roughly 40 and 66 billion suns, and that spread isn't sloppy reporting. It is the gap between two measurements that flatly disagree. One equation covers every rung. Almost nothing else about them matches. Start at the bottom with the class we aren't sure is there. Yakov Zeldovich and Igor Novikov floated the idea in the mid-1960s, and Stephen Hawking developed it properly in 1971. In the first fraction of a second after the Big Bang, the universe was dense enough that a patch of space slightly lumpier than its surroundings could collapse where it sat. No star required. A black hole born that way has no minimum size, so its mass depends entirely on how big the lumps were. So why keep chasing something nobody has ever seen? Because that freedom is the whole appeal, and decades of searching have closed most of the range without closing all of it. One window is still open, the band astronomers call asteroid mass, from around 100 billion tons at the bottom to 1 million times that at the top. Even at the heavy end, the horizon would be smaller than a speck of dust, and at the light end far narrower than an atom, so no instrument we've built could catch one drifting past. Hawking's own maths sets the floor. Below that band, a primordial black hole has either finished evaporating already, or it is still leaking gamma rays hard enough that our telescopes would have caught the glow. Objects in that window could be all of the dark matter, or none of it. After 50 years of hunting, the count stands at 0. The class we genuinely understand is the one dying stars make. When a star far heavier than the Sun exhausts its fuel, its core falls inward, and past roughly 2.5 solar masses nothing known can hold the collapse. Electrons fail. Neutrons fail. Where neutron stars stop and black holes start has been argued over for decades, which is why a signal from the 29th of May 2023 mattered so much. LIGO recorded a merger in which one object weighed about 3.6 solar masses, parked in the disputed gap, too heavy for a comfortable neutron star and too light for a comfortable black hole. Go the other way, and the numbers keep getting revised upward. Cygnus X1, the first black hole most people ever heard of, was remeasured in 2021 by James Miller-Jones and colleagues using radio astrometry, and it came out at 21.2 solar masses. Then in April 2024, the Gaia mission turned up a sleeping one about 2,000 light-years away in Aquila at 33 solar masses, the heaviest stellar black hole known in our galaxy, orbiting a star almost bare of heavy elements. That detail is the clue. Stars pour in metals blow less of themselves away on the wind, so they leave fatter corpses. Now the awkward rung. Above about 65 solar masses, theory says stars can't make black holes at all. The core gets hot enough that its own light starts converting into electron-positron pairs. The pressure propping the star up drains away, and the whole thing blows itself apart without leaving a remnant. Studies of collapsing stellar cores put that pair instability gap at roughly 65 to 120 solar masses. Above it, for a long time, the next confirmed objects were millions of times heavier, so the middle of the ladder had a hole in it running from about 100 solar masses to 100,000. So where were the ones in between? Not hiding for want of a search. You weigh a black hole by watching things orbit it, and a mid-sized one's grip on its neighborhood is a punishingly small target to resolve at any real distance. Most of them aren't eating either, so they never light up in X-rays. Small, dark, and quiet, which is close to the perfect way to hide. Two results broke it open. On the 21st of May 2019, LIGO and Virgo caught a signal that was over almost as soon as it started, and the analysis published the following year said two black holes of roughly 85 and 66 solar masses had slammed together into one of about 142. At least one of the pair had no business existing under the pair instability rules, and the remnant was the first clear detection of an intermediate mass black hole. Then, in July 2024, Maximilian Habel and colleagues at the Max Planck Institute for Astronomy published the other kind of evidence in Nature. 7 stars near the heart of the cluster Omega Centauri, picked out of a long baseline of Hubble imaging, are moving fast enough to demand at least 8,200 solar masses of something invisible holding them in. That one is still being fought over. A 2025 reanalysis of the same cluster argued the motions do not require a black hole at all. The record, meanwhile, has kept climbing. In July 2025, the LIGO, Virgo, and KAGRA collaborations announced GW231123, a collision of black holes near 100 and 140 solar masses that left behind a remnant of roughly 225. Climb 3 more orders of magnitude, and the objects change character entirely. Supermassive black holes, millions to billions of suns, sit at the center of essentially every large galaxy, and we have photographs of 2. M87s, imaged by the Event Horizon Telescope in 2019, comes in near 6.5 billion solar masses. Ours, Sagittarius A star, imaged in 2022, weighs about 4.3 million and lies about 27,000 light-years away. And we know that figure because Reinhard Genzel and Andrea Ghez spent decades clocking individual stars whipping around it, work that earned them a share of the 2020 Nobel Prize in Physics. How these things got so heavy is unsolved. Building one by ordinary feeding takes time, and the early universe stubbornly refuses to supply it. In August 2025, Anthony Taylor's team at the University of Texas at Austin confirmed the most distant black hole yet found. Their best estimate puts it at a few tens of millions of solar masses, and the top of their range reaches 300 million. The galaxy around it is one we see as it was 500 million years after the Big Bang. Something got a head start, and we can't say what. Which brings us to the top shelf. Past 5 or 10 billion solar masses, depending on whose paper you read, the label changes to ultramassive, and Ton 618 has owned that category in the public imagination for years. It surfaced on photographic plates at the Tonantzintla Observatory in Mexico in 1957 and was only later recognized as a quasar. Its light has been traveling for about 10.8 billion years, and it burns with the output of something like 140 trillion suns. In 2004, Ohad Shemer's team measured the width of its hydrogen beta emission line, and the mass that falls out of that width is 66 billion suns. In 2019, Zhu Ji and colleagues went back to the same data, ran the calculation on a different line, carbon-4, and got 40.7 billion. They can't both be right, and the disagreement is the honest state of the field. These masses come from the width of a spectral line and a calibration, never from watching anything orbit. Even the lower figure is absurd. That horizon has a radius near 800 astronomical units, 20 times Pluto's distance from the Sun, and light needs about 9 days to cross it. There's a ceiling up there, and Ton 618 is pressed against it. In 2016, Andrew King calculated that beyond roughly 50 billion solar masses, a black hole can no longer keep a working accretion disk, because the outer disk crumbles into stars instead of falling in, at which point the quasar shuts itself off. Mergers with other black holes could still add mass, but the bright feeding is over. His limit only stretches into the hundreds of billions for a hole spinning at the maximum rate allowed. So the biggest object on the ladder sits right at the edge of what the physics permits, measured by a technique with a factor of 2 spread. Better numbers are starting to arrive from a different direction. In August 2025, Carlos Milo Carneiro's team weighed the black hole in the cosmic horseshoe lens at around 36 billion solar masses. They got there by combining gravitational lensing with the measured motions of stars, a far cleaner way-in than any emission line can deliver. Line the whole ladder up, and the mass range covers close to 30 powers of 10. At the bottom, maybe, a horizon narrower than an atom with a mountain's worth of mass behind it. At the top, a hole you could drop the solar system into and lose it. All of it falls out of one solution to Einstein's equations, worked out by Karl Schwarzschild in December 1915, while he was serving as an artillery officer on the Russian front, mailed to Einstein in a letter, and published a few months before Schwarzschild died of a disease he'd contracted at the front. He treated the result as a curiosity, a place where the mathematics misbehaved. He was writing down the size of every black hole in the universe. And the largest one on our list is so big it breaks the accounting. Our best model of how these things feed says it should have quit growing long before it got there.